Last class we have started the basic equations in thermodynamics. We started with this, all of you are aware of it. Then we introduced the second law, which is basically we said it is this, and that is what introduces two new parameters, which are, one is the entropy and another is the free energy. And we said the stability of all the phases is actually related to the free energy. And let us go a little details into this and see how to represent free energy as a function of temperature, and how does that give us information about the stability of phases. To understand that, first let us look at how to evaluate the H and S. If you look at it, we all know that dH is Cp dt. This every one of you know. So as a result, I can write it as H is integral Cp dt, where t goes from, let us say, 0 to t. Usually enthalpy, in thermodynamics we have what are called standard states. So when I want to, all these are actually relative numbers, because so you need to set up some particular condition which we call it as a standard state, and that condition that we set up is at a temperature called 298, which is room temperature. So we define H at 298 as 0 for most of the materials. You can even change that depending on the particular condition. You can change this number depending on the particular circumstances, but usually we assume H at 298 as 0. And if you assume that and then try to plot
here, H 298 equal to 0, so if we integrate from 0 to 298,
yeah, so that is why this becomes negative. So that is what we are going to see it right now. So if you plot Cp as a function of temperature, we know that Cp goes something like this, a typical S curve, all of you are aware, and Cp goes to 0 at absolute 0, this is 0. And we also know that the maximum value we reach is approximately around 3R. And now if I try to plot H as a function of temperature, you would see the H as a function of temperature would go something like this, where here at 298 it is 0 and below 298 actually it is negative. So in principle, if I define H at 0 as 0, then obviously this everything will be in the positive quadrant. So this is a typical way of representation of the H, and once I know H is represented that way, I can also start defining S, because S, the way we define the second law, the entropy term, is ds equal to q by T actually, and Q at constant pressure is known to be as dH. So actually ds is dH by T, and that also leads you to the other equation, which is very useful as we go along. We see this because this becomes useful when we are defining the free energy more easily. So you can see that ds is dH by T. If ds is equal to dH by T, then I can simply write ds equal to Cp dt by T, because dH I have already defined it as Cp dt, isn't it? Yeah.
Sir, why don't we take H 0 as 0?
You can always, because 0 is a term which is an ideal term which you rarely reach. And if somebody has to experimentally measure anything, we are accepting a few physicists. Most of us who deal with either chemical engineers or metallurgical engineers or material scientists, most of us deal with room temperature. So as a result, we start at room temperature. So most of the applications demand temperatures beyond room temperature, not really sub-zero to a large extent. So as a result, and understanding this, and in principle even if you take it as that, it is only a scaling factor, things get changed. So as long as one thing you know, then you can start calculating what is it at other temperature. It is not a big problem, it is only changing some kind of number. Some reference is required, so this is a more easier reference for us to deal with. Room temperature is a easier reference. Once I understand this, I can even write now as S as integral Cp dt by T, again going from 0 to T, let us say. And this is where we define a third law of thermodynamics, where S equal to 0 at T equal to 0. So that integral we assume it to be 0, and because we also know that the Cp itself goes to 0, there are no vibrations. When there are no vibrations, there is no thermal entropy. There is no thermal entropy, please remember. We will come to the configurational entropy a little later, and this configurational entropy need not have to go to 0 at absolute 0. Thermal entropy is 0 because there are no atomic vibrations. If there are no atomic vibrations, there is no randomness created by atomic vibrations. So the crystal is perfect, atoms remain where they are, and they do not move, and as a result they do not cause any randomness inside the material. So this is how we basically define this, and in principle I can also plot, if I plot S versus temperature, S versus temperature would S versus T, if you plot S versus T also would have a curve like this. Basically it comes from the Cp type of curve. It would be something similar to the Cp curve, and it goes to 0 at absolute 0, and then it keeps on increasing, and not only keeps on increasing, if you carefully observe ds by dt, if I take ds by dt is what? Cp by T. So because it is Cp by T, in principle at very high temperatures this slope should come down as you increase the temperature, but there is a small hitch here, that Cp is also increasing with increasing temperature. If Cp was constant, then I can say the slopes keeps on decreasing as the temperature increases. Entropy increases with increasing temperature, but what we are talking is the slope of this entropy. That means the rate at which this entropy increases with increasing temperature is going to decrease as the temperature increases. So initially it will be a steeper curve, and later it becomes a kind of a shallower curve, and in principle this curve will never become let us say 0. That means the slope of this curve will never become 0. It will become 0 only when either this, I mean Cp becomes 0, and Cp never becomes 0 at higher temperature, we know pretty well. So it will still have a low slope, but it will maintain certain positive slope. So not only S is positive, ds by dt is also positive. This is a very important thing that you need to understand. The rate of change of entropy with temperature is always positive, because Cp is positive. The lowest value that it can go is 0, and that is only at absolute 0. And at absolute 0 we do not really talk about rate of change, because it is one single temperature. So as a result you can see that, but what is important is ds by dt decreases as T increases, because Cp does not increase at the same rate as T. If you remember, some of you might have gone through how we express the Cp, a plus bt plus Ct to the power minus 2. So there is an expression which is used for Cp to fit that particular curve which we have drawn before. How does the Cp change with temperature? So it fits to almost at in a very small range. When I look at it, it can be fitted as a plus bt, but if you take the whole range, then you see particularly at low temperatures the Cp change with temperature is very small. So this is one important point that you need to remember, and we will keep bringing these concepts as we go to the free energy. Now let us look at the free energy, and that is the most important thing for us, because as we said the whole stability is dependent on free energy. Now let us try to expand this I said just now G is H minus Ts, and if I write it more elaborate, this H we know already is E plus PV. So I can write it as, using these two equations, for example, I can write it as E plus PV minus Ts. Now let us differentiate this. If you try to differentiate it, I can write it as dG equal to dE plus PdV plus VdP. Am I right? Because it is a partial differentiation, and minus T ds minus S dt, perfect. Now if you look at it, dE plus PdV is dH. We all know that dH is defined in terms of that, and TdS is dH. Where did we define? Okay, somewhere here. TdS is dH. So in principle this is dH plus VdP minus dH minus SDT. So as a result these two get cancelled, and you end up in an expression that dG is VdP minus SDT. This is a very, very profound Maxwell's equation, and that leads you to a lot of interesting things, such as what is called, anyone knows, we talk about Clausius-Clapeyron equation. Clausius-Clapeyron equations comes from there. We will see how does it come. So this tells us that at constant pressure, if I take dG by dt at constant pressure is what? Is minus S, and S is never negative. We have already defined S is what? The degree of randomness, and the degree of randomness can never be 0. It can maximum, it can be minimum, it can be 0. The lowest value of S can be only 0, and then it will be more than 0 at all other temperatures. As a result, because S is positive, dG by dt has to be negative, because there is a negative sign before the S, and if the S would have been negative, then the dG by dt would have become positive. So dG by dt is always, as I can write, as S is positive, dG by dt is always negative. What does that tell me? It tells me that if I plot G versus T, let us say any material like this, I try to calculate what is the free energy of this material and how does it change as a function of temperature, and if I plot that, let's delete this, because this we have gone through. I am sure you are aware of this. So if we now plot G versus T, how should the free energy curve look like? Okay, so it decreases. Is this fine? I would say it is not fine. Yes. When will this be fine? Yes, when S remains constant, this plot is perfect. What does this tell you? It tells you that it is a linear relation. A linear relation means what? Slope is constant. What is the slope of free energy versus temperature? Slope is minus of entropy, and this is decreasing, fine. So the minus is taken care, but the slope is constant there. If the slope is constant, it tells you that the entropy is not changing as a function of temperature, but we know pretty well that the entropy changes with temperature. So now can you tell me how should it change? So this is wrong. So what is the best way? Yes, it should decrease like this, to an extent that as I come closer and closer to absolute 0, the slope should tend towards 0, because at absolute 0 entropy is 0. So the slope of free energy versus temperature should go to 0 at absolute 0. This slope is 0. At any other temperature the slope is higher, and the slope keeps on increasing. For example, if I look at slope here, I draw a tangent, let us say here, and I draw another tangent here. This tells me the slope at this point, this tells me the slope at this point. You can see the slope here is higher, the slope here is lower. So at a higher temperature, at any higher temperature, the slope of G versus T is going to be higher, and that is what higher in a negative sense. Keep that in mind. Definitely we are the whole curve is the slope is negative. At all temperatures slope is negative. At only one temperature the slope goes to 0. At no other temperature slope is either 0 or negative. This is the temperature where the slope goes to 0. At any other temperature slope is negative. So that is what you see, this is negative, and that absolute value of the slope is the entropy, and that absolute value of the slope, because it is higher at higher temperatures, you will see this is the typical nature. And now if I find out what is this value, can you tell me what is G at absolute 0? Depending on what is there on the right side, you would H, very easy, G equal to H at T equal to 0, isn't it? So this value is nothing but H, whatever it is, and at any temperature if I draw a tangent and extrapolate this tangent to the absolute 0, for example, if I extrapolate this tangent to this value, this intercept is what? H, because is this G is H minus Ts and slope is the S, we are talking of dG, and this value is the intercept. So you will always get the intercept as the H at, so at different temperatures, and in principle you can see as I increase the temperature the slope is increasing, as a result the intercept also will increase, which also gives you an idea that the H increases with increasing temperature. So where this particular tangent is going to intersect the vertical axis is going to keep on increasing, and that gives you an idea that the H of any material, H of any phase that we are talking is going to increase with increasing temperature and at the same time. So not only H increases with temperature, we also see S increases with increasing temperature and G decreases with increasing temperature. Fine. And in principle if I write both G and H in the same thing, you would see we have just now seen H goes something like this, and you see G would go something like this, and at absolute 0 this is the H value, and this is increasing whereas this is decreasing, and this difference between these two is what? Ts, very easy, and this difference keeps on increasing as we go to higher and higher temperature. That tells you that both the T is increasing and S is increasing, as a result you would see the difference keeps on increasing. So in principle we can plot like this. Now let us try to understand, is this all clear? So we should know how to, so from now onwards whenever you draw free energy, be very clear that G cannot be a straight line as a function of temperature, which you would have possibly drawn a number of times before. So this has to go into your mind that G, the slope of it being nothing but entropy, it can never be constant, and entropy is never constant. So once this is clear, let us try to understand what is the necessity of G. Why should people introduce this concept called G? Earlier people thought the stability of phases, when do I say something is more stable? I compare, let us say, two things. When I compare two things, let us say a simple case, let us say I am talking about aluminum. Aluminum, it can be a liquid, it can be a solid, it can be a gas. Let us say I am comparing a liquid and a solid. If I consider the enthalpy of liquid and the enthalpy of solid, what is higher? Liquid is higher. Why is it higher? Because the Cp of the liquid is always higher than the Cp of the solid. Heat capacity of a liquid is always higher than the heat capacity of the solid. Why? The vibrations are more in a liquid when compared to a solid. As a result, Cp is higher, and if Cp is higher, because H is nothing but integral Cp dt, you can say H of liquid is always higher than H of solid. So as a result, if I say that at melting point solid is changing to liquid, it is going from a lower enthalpy state to a higher enthalpy state. Now a reverse transformation, where the liquid is transforming into a solid, it is going from a higher enthalpy state to a lower enthalpy state, isn't it? So as a result, I am seeing that below the melting point a phase with a lower enthalpy is stable, that is the solid. Above the melting point a phase with a higher enthalpy is stable. So if I use enthalpy as a stability criterion, I have difficulty in the sense that I cannot say a phase with a lower enthalpy is always stable. I cannot say this, because I myself I am able to see that the liquid is stable above the melting point and liquid always has a higher enthalpy. So how can I say that this phase having a lower enthalpy is always stable? Same problem comes if I take entropy. If you see entropy of a solid and entropy of a liquid, entropy of a liquid is again higher than that of the solid. So I can say liquid entropy is higher than solid entropy. Again I am in the same situation, that I can never say the phase with a lower entropy is always the stable, or the phase with a higher entropy is always stable. I can see this reverse phenomena happening. Above the melting point the phase with a higher entropy is more stable, and below the melting point a phase with a lower enthalpy is more stable. And if I take this lower entropy phase or a lower enthalpy phase which is a solid and take it above the melting point, I cannot retain as the solid. It immediately starts transforming into a liquid. Though it has a lower entropy and lower enthalpy, it does not want to remain. So that is where people thought, what is that would help us to be able to understand the stability in terms of one parameter, and that turns out to be free energy. And how to understand that? If I try to now plot G versus T for this liquid and the solid, let us try to superimpose the free energy of the liquid and the free energy of the solid on this curve and see what happens. For example, I can draw a curve something like this and then say this is the free energy of the solid. It is satisfying whatever I have said before, that its slope goes to 0 at absolute 0 and its slope keeps on increasing in a negative sense as the temperature is increasing. This is fine. Now if I superimpose a liquid free energy curve on this, how should that be? What should the characteristics of that with respect to this curve? At 0
liquid will have higher free energy.
higher free energy. And why a higher free energy? Because it has a higher enthalpy. At absolute 0 free energy is equal to enthalpy, and the liquid enthalpy is always higher than the solid enthalpy. Next, second thing is that its slope should be higher. So if the slope is higher, then I will see that the curve will be something like this. Whenever you have two curves, one with a higher slope than the other, obviously they both have to intersect. It is not possible to have two curves with different slopes not intersecting. So as a result, you would see that this is nothing but H of the liquid at absolute 0, this is H of solid at absolute 0, which is higher, and now this is the curve for the liquid. And when I look at this curve, it gives me very interesting phenomena. What is that interesting phenomena? There is an intersection here, isn't it? And if I look at what is there above the intersection, what is the nature of the curves above the intersection, and what is the nature of the curves below the intersection, what you see is that above the intersection the liquid curve is always below that of the solid curve. That means liquid has a lower free energy than the solid above that intersection, and below the intersection if I look at it, the solid is always below that of the liquid, isn't it? This is the solid curve, this is the solid, this is the liquid. So the solid curve is below that of the liquid, so that means the solid has a lower free energy than the liquid below the melting point. And above the melting point, I am sorry, I have already used the term, this particular point is what we call it as the melting point. That particular intersection of the two free energy curves is, we call it as a melting point. Why we call it as melting point? Because beyond the temperature I see that the liquid free energy at all temperatures is lower than the solid free energy, and because it is lower I can now say the liquid is more stable above the melting point because it has a lower free energy. And similarly when I come to the temperatures below the melting point, I can see that the solid free energy is lower than the liquid free energy at all temperatures. So at all temperatures below melting point I can always say the solid is more stable because it has a lower free energy. Now we have one parameter which tells you that if that is lower, the phase is stable, and that parameter is this free energy, Gibbs free energy. So if the free energy is lower, then it is stable. If the free energy is higher, then it is what we call it as what do we call it? It could be metastable or unstable. This is what, that's where we end up into the regime of kinetics. Always we say thermodynamics tells you what is feasible, it does not mean that it would happen. It is like this. For example, if I look at this, this is some state called A, this is another state called B, let us say, and if I am plotting this in terms of the free energy, the free energy of the A is higher than the free energy of the B, but it does not mean that this A will immediately go into B. For example, a simple example could be even this. If you look at this duster, if I leave this duster on this table and I keep this duster in this form, what is having a more lower free energy? This form, obviously, because the Cg is lower. If the Cg of it is lower, I can say yes, this has a lower energy state, and if I am keeping it here, it has a higher energy state, but I can keep this like this forever until I push it, I can keep it forever. That means this higher energy state is able to remain in a higher energy state forever almost until somebody gives you an activation. We call it as activation. That is what is this called activation barrier. This is what we call it as delta G star. We will talk about it more later, but just this gives you. And how to understand this? If you look at it, if you take this state, this is the duster, and if I say that I join all these both the diagonals, and I say this represents the free energy, that is the Cg of that. If I say that represents the energy of the system, and from there it comes to this level where I join again and say this represents that energy, and between these two states, when this is going from this state to that state, you come to a state like this which is inclined, and that state, if you carefully observe, and that state if you join, you see that the Cg of that is higher. So it is going from a lower energy to a higher energy, and then further coming down. That is what we call it like an activation hill. And so it goes to, and this particular state is what we call it as unstable state, because if you keep this in this state, it will not remain, suddenly it falls off either this direction or that direction. So that is the interesting thing about unstable state, either it comes to a metastable state, this is the metastable state, this is the stable state. So it can either shift this direction or this direction depending on in which direction your force is. So you can see that this is the difference between thermodynamics and kinetics. So thermodynamically we say that this is more stable, in principle this should become this, but it is not happening. Many of you might have heard of all of you know about steels, I suppose. If I look at the microstructure of steel, what would I see in the microstructure of steel? Perlite. What is perlite? Ferrite and cementite. Do you know that this cementite is not a stable state? It is a metastable. In principle, if I take this cementite to a higher temperature and heat it, it becomes ferrite or alpha or iron plus carbon, graphite. In principle, cementite is not stable, but we see the steel at room temperature, cementite exists forever, for ages, nothing happens to it. The cementite remains as cementite. You make a mild steel and then just leave it and it remains. Why? Because it has a large activation barrier for that Fe3C to split into iron plus carbon, and unless you provide that activation barrier it would not change, and as a result that activation barrier you are providing by heating the sample to a higher temperature. In fact, that is what we do when we convert one of the cast irons into another cast iron. Have you heard of that? There is a treatment. What is the treatment called? Malleabilization, where you take a white cast iron which has a cementite network, cementite phase, and you heat it to about 900,000 degrees centigrade, where that cementite splits and gives you a graphite. So in principle one can, even people when they do spheroidization of steels, if they do spheroidization of steels for a very long time, you would see that cementite spheroids that are forming can even split and you get ferrite plus graphite. People have done this and seen. So in principle, if you can provide that particular activation, any metastable state would like to go to a stable state, otherwise it would remain in a metastable state forever. So this is the difference between thermodynamics. Thermodynamics tells you that this is a stable state. In principle the system would like to be here, but it can still remain here because you have not provided. So it is like a local minima. Okay, people talk about local minima, this is kind of a global minima. So it remains in a small trough there, and if you push it, it will go up and then come down. So it is like that. So you can see that this is the basic concept of the free energy. So we have now defined that this free energy is a concept which we can use for understanding what is stable and what is metastable. I can only say it is meta. I can say, for example, I have to tell you this again clearly, that if I am at this temperature, that means I have taken a solid, heated to this temperature. What should happen when I heat the solid to this temperature? It should become a liquid. Why it should become a liquid? Because solid has this free energy at that temperature, liquid has this free energy at this temperature. So liquid has a lower free energy than that of the solid. This I can call it as a GS, this I can call it as GL. GL is lower than GS. In principle solid should become a liquid. It is possible that solid can still remain as solid, which we call it as a metastable solid, if the conditions are not ripe enough for the solid to become a liquid. In case of solid to liquid, this does not happen because solid to liquid transformation is much faster than liquid to solid transformation. You see the reverse happening more easily. If I take a liquid, cool it to a temperature like this, you can see that the liquid has a higher free energy, GL is higher, GS is lower. In principle liquid should become a solid. but there are many cases where liquid does not become a solid and remains as what is called an undercooled liquid, and in fact that is the principle behind getting a glass. We will slowly see a little later. For example, maybe the time has come, so let us see it right now. Or no, let us leave it, unnecessarily we are deviating. We will talk about liquid to glass transition a little later. We will see. So you can see that this liquid can remain as liquid. The reason is, from a liquid, if you imagine, for a solid to nucleate, if you have a whole liquid, bunch of liquid, and you have a solid coming out of the liquid, you have a problem. What is the problem? It has to create a new surface. This surface did not exist before, isn't it? That surface has to be created. Though the liquid has a higher free energy than the solid and liquid wants to transform into a solid, you would see that because this solid, the new surface, which we call it as an interfacial area between the liquid and solid, and that is represented by one what is called interfacial energy called gamma SL, and every surface, every interface is associated with certain energy. That energy has to be spent. That energy you have to create that particular surface, and to create that surface you need to have certain energy with you, and if that creation of the surface is difficult, the liquid does not become a solid. And if you have seen what are called cooling curves at some stage, have you seen how does a pure metal liquid become a solid? If I take a furnace, melt a solid, put a thermocouple there inside, and then switch off the furnace, and then watch how the temperature of this liquid is changing as a function of the time, and I plot that T versus small t, and I usually see this kind of a thing for a pure metal. Many of you might be aware of this. And why does this happen? In principle, I expect that it should be like this: liquid, this is the liquid, and once I bring it to melting point, this is the melting point. This liquid should transform into a solid at that temperature, but the liquid does not transform to solid. This liquid to solid transformation does not occur suddenly here at the melting point, but the liquid had to be cooled to below the melting point to some temperature before this liquid actually starts transforming. Why is that? That is because when you cool this liquid from this melting point to a certain lower temperature, this what we call it as undercooling, this is what we call it as delta T, undercooling. When you provide that undercooling, what is happening to the free energy? Let us say from the melting point I have brought to this temperature. Once I bring it to this temperature, there is certain what is called driving force. At the melting point, what is the driving force? 0, and that is what we define it as equilibrium. So in a single component system, equilibrium is defined as that where the free energy of both the phases is equal. That is what it is at the intersection. At the intersection, G of S is equal to G of L. This is the definition of equilibrium, and so we say this is the melting point where the free energy of both the phases is equal, and if the free energy of both the phases is equal, for any of the transformation either from liquid to solid or solid to liquid, there is no driving force. If I take a liquid, keep it at the melting point, in principle it will not become a solid. Similarly, if I take a solid, heat it up to the melting point and just hold it there, in principle it should not become a liquid, excepting if you heat it by a very small amount. It could be let us say third decimal in terms of the temperature. You need some small driving force for this solid to become a liquid. Similarly, for the liquid to become a solid, you need a driving force. The only difference between a solid and a liquid can be easily understood if you take an ice cube from a fridge. Let us say somehow you have taken an ice cube without holding it and you are just leaving it in the air, let us say, and the atmosphere is above the 0 degrees. So this ice cube has to melt. How does it start melting? Where does the melting start? Surface, anything else? Corners. First is it starts, that is why you will see that the ice cube, the corners start becoming rounded first. Why is that so? Because then the next stage is actually the edges, after that actually comes the surface. The reason is the surface energy is highest at the corner. Why is that so? Surface energy comes from what is called broken bonds. If you take a material, for example a solid, if I take inside the solid, ice for example, if I am taking ice, ice has a structure. Do you know what is the structure? What is the crystal structure of ice? Little louder. HCP, hexagonal. It is a hexagonal structure. So this hexagonal structure, if I think of the atoms which are on the surface, in a hexagonal structure you remember what is the coordination number? 12. That means every atom should have 12 nearest neighbors. So you will have 6 in the plane, 3 above the plane, 3 below the plane. Am I right? Now if you imagine that there is an atom sitting here, that atom has 6 atoms in that plane, 3 atoms below that plane, but there are no 3 atoms above that plane. So that means that particular atom there has certain number of broken bonds. In principle it is 3 by 12, 3 by 12. Out of the 12 bonds that it should have, 3 bonds are not there. As a result, that particular atom is at a high energy state, because it is not having all the atoms which it is supposed to have. Whereas if you think of an atom which is at the center somewhere here, it has all the required number of atoms around it as per the coordination number. So the atom here is in a much better state when compared to atom here. So this is at a high energy state. So similarly, if I take this corner would have more number of broken bonds. And if I now think of a solid, and now consider these corners and these edges and this surface, you can easily see the corner would have more number of broken bonds, the edge would have next level, then the surface, then the atoms inside. So energy levels go by that hierarchy. Any atom sitting at the corner of a cube would have the highest energy, and that atom, that particular region, because it is at a highest energy, it wants to transform first to something which is a lower energy state. Why? Because I am at a temperature above the melting point, I am at room temperature. I said at room temperatures the liquid is more stable than the solid. So ice cannot remain as ice, it wants to transform to a liquid. So that particular region which is the highest energy immediately transforms. Then comes the edges start becoming rounded, and then the surface, and so the actual melting starts from the surface and goes into the interior. Why? Because the surface area is available for it. Now if I take a liquid and try to make it a solid, where is the surface available for the liquid? Until you think of, I pour this liquid into a mold, sir, the mold is there as a surface for the solid to nucleate, and that is the reason why in most of the casting process the solidification starts at the mold interface, mold liquid interface. And there are interesting people who do what is called containerless solidification. In our department there is a professor, I do not know how many of you have heard of, Fani Kumar. He has set up what is called a levitation facility. It is very interesting to see, please go and see. This is the first levitation facility in the country, where you take a piece of metal like this, you levitate it, it is standing in the air now, and then you heat it using a, let us say, an induction heating or any heating, let us say electron beam heating, any heating, you can heat it and melt it. Once it is molten, it becomes liquid, and this liquid droplet is floating in the air now, and you switch off that heating source, now it starts cooling, and you can actually observe how does it solidify, where does the nucleation start. Very, very interesting phenomena. A lot of people have struggled to understand this whole concept of nucleation. Where does the nucleation start? And in fact, long back there is a great man by the name Turnbull who has done what is called droplet immersion technique. What he has done is he has taken a liquid metal, allowed it to go through a nozzle and made it into a stream of droplets, okay, an emulsion of droplets by kind of atomization kind of thing. When you do this, droplets of different sizes form, and different sizes, if you look at it, the smaller droplets will have lesser number of heterogeneous nucleating sites, because people knew for quite some time that this kind of a solidification is happening only because of heterogeneous nucleation. Otherwise, in principle it should be this. Why? Because when I undercool, I am providing sufficient energy, and when this energy is equivalent to the surface energy, that is when the solidification will start. Until the energy that I have in my pocket, it is like you want to spend something, you should have something in your pocket, isn't it? Unless you can say I can use my credit card, sir, always. So otherwise you should have something. So here also is situation. So unless you have a driving force, some energy available with the liquid, excess energy that is available with liquid, it cannot spend that. Okay, it should have sufficient excess energy that is sufficient for creating a new surface. That is when solidification will start. So the liquid will keep on undercooling until you get sufficient energy that is available. We are going to slowly, maybe next class, relate this to this. There is a relation between delta G and delta T. We will see that also. What is the relation? And you will see that once I provide sufficient undercooling, at least graphically you can see, as I increase the delta T, because as I go more and more away from the melting point, this is increasing. I can see that, but in principle one can calculate that also. So I say that at a given delta T there is a certain value of delta G, and if that delta G is equivalent to that of the surface, that is why if you remember, anybody who has done some nucleation, he would write this expression. For a spherical nucleus that is coming out like this, we say there are two terms, 4 pi r square gamma plus 4/3 pi r cube delta GV. When I am creating a spherical nucleus inside a liquid, this is the energy that is given out, this is the excess energy of the liquid, whereas this is the energy that you need to create. For a spherical particle, this is 4 pi r square is the surface area, multiplied by this is per unit area always. This is the energy that you need to create, this is the energy that you are providing. So you would see that unless this is equal to this, you would never see the transformation taking place in such a way that this overall delta G has to become negative. When this is negative, then solidification will occur. If that is 0 or positive, solidification will not occur. So that is the reason why we need certain undercooling. That is the reason why people saw that usually you do not see this. This is what we call it as homogeneous nucleation, this is what we call it as heterogeneous nucleation. Heterogeneous nucleation occurs when there are already certain particles available in the liquid. In fact, that is one of the concepts of what is called grain refinement, inoculation. People regularly use this term. So if I add certain particles into my liquid and pour it into the mold, now these particles, if they have a similar crystal structure as that of the solid that is coming out, then this surface energy is very low. Whenever the structure is similar, you must have heard of what is called epitaxy. Anything can grow very easily if the structure is similar. So you would see that if I add particles which have the same structure, same or similar crystal structure as the solid that is coming out, you would see that it would easily nucleate. So that is why there are specific nucleating sites for specific type of solids. You do not add everything for everything. For example, in aluminum alloys, we know, for example, there are something as TiB2, titanium boride, titanium carbide. TiB2 is hexagonal. If you carefully observe, there is a similarity between hexagonal and aluminum. What is the crystal structure of aluminum? FCC. So, what is the similarity between FCC and HCP? Closed packed structures, yes. Anything in terms of any planes, is there any similarity? Atomic planes?
HCP has got AB.
Any plane of HCP, does it have any similarity with any plane of FCC? Because why I have to say this is nucleation always occurs on a plane, it cannot occur anywhere, it happens on a surface, that is why the planes are important. There is a certain plane in HCP which is exactly similar to another plane in FCC. How much of crystallography you know? 100, sorry. What is the closest packed plane in HCP? What is the indices of it? 0001. Okay, the 0001 plane is similar to another plane in FCC. Can you think of it? 111, perfect. So, the aluminum can nucleate on that particular 0001 of titanium boride very easily with its 111 plane parallel to that the basal plane of the TiB2, and then the nucleation can occur. I think we will stop with this. Thank you very much.